Hello, everybody, and today we will talk about what's called configurable logic cells, CLC, configurable logic cells, CLC, by Microchip. Actually, configurable logic cells is amazing feature which many companies, such as Microchip, like implemented within their microcontroller. So this one here, for example, is PIC 16F 1619, and some other microcontrollers as well. They do include this feature. They provide you with additional feature or peripheral, if you wish, that can operate independently from the microcontroller core. Okay, so you just set it up from within the configuration bits of the microcontroller, and you don't have to write any code. Right now, this is running without any code. Okay, just by configuring, by configuring the CLC or configurable logic cell. Okay, let's look at how, for example, what is the difference, or how the FPGA, which is field programmable array, FPGA arrays, right? Programmable arrays. The difference between FPGAs and CLCs, configurable logic cells, is that FPGA, they are of very high number of cells. Like they encompass thousands, sometimes tens of thousands of arrays of logic cells, right? But this one here, since they are giving you the core, all the peripherals of microcontroller, which are the dreams of embedded designers like myself. It's our dream, actually. So we don't expect Microchip to give us thousands and tens and hundreds of thousands of like field logic gates. Okay, we will be happy with maybe 50, 20, several hundreds, or maybe few logic cells. Okay, right now, as you see, we have OR. We have like those cells are OR gates. This is the JK flip-flop. You can actually select from here. You can select the logic, the kind of logic you want. You can, for example, include the D flip-flop. You can have with set reset, and or, and like it's really very like amazing, latch, SR latch, or XOR logic. And why do we need sometime hardware based logic cells within the microcontroller? Okay, because mainly because for speed, because sometimes certain applications, they are speed hungry. They want very fast processing. And some, believe it or not, like sometimes the code, even in assembly code, even in C language or assembly, that talks to the hardware directly, the assembly code, sometimes it's impossible to perform certain tasks with the code. So that's why we need to have those kind of configurable logic cells, or you can call it the FPGAs of Microchip, or and FPGAs that are embedded within the microcontrollers. But of course, those companies will not give you the benefit of having both the microcontroller and FPGAs, because it's going to be very expensive. They give you some of the FPGA features with complete features of fully fledged microcontroller, very high intelligent and sophisticated features, or like peripherals, if you wish, right? So let's see how this thing work. Like, for example, now I configured the timer. Which I'm using timer 6 of this guy, 16F, PIC 16F 1619. I am using the timer 6. I'm using the configurable logic cells, unit number 1. Okay, and I'm using the interrupt module. I'm not using, but I'm using the system, of course, and the pin module. In here, actually, how you manipulate, by just clicking on this, you invert it to NOR. Now it is OR with 4 inputs. Okay, So what's the deal here? This one here is, remember, this is the output from timer 6. So timer 6, if you go to timer 6, this one, timer 6, you see that I set it to oscillate at a cycle of 1 second or 1000 millisecond. It means every 1 second it goes high and low, then another second high, 50% duty cycle. It means 500 millisecond high, 500 millisecond low, 500 high, 500 low. So this is called a cycle, a square wave with cycle of 1 second or 1000 millisecond. And that's what it causes. The CLC logic cells. It causes the LED to blink on and off. Okay, let's analyze this beast, how this beast is working, the miniature beast. Okay, so basically this is the timer 6. The timer 6 is set to oscillate at like to provide a square wave with a duty cycle of I'm sorry, not duty cycle, with cycle period of 1 second. I'm now because I've been using duty cycle nowadays a lot, so it's on my tongue, so it is actually a cycle, a square wave. This timer 6, now it is delivering to us, or it is making us for us a square wave with cycle of 1000 millisecond or 1 second. Okay, what that means is on 500 millisecond and off 500 millisecond. Okay, so if we go to data sheet, this one here is I'm using this one here is the hardware flip-flop, okay, from Texas Instrument I'm using. And let me show you here what I am doing actually. Okay, this is another microcontroller. I'm just playing games here. Okay, what I did, I caused this microcontroller to provide me with a square wave with cycle of a half second or 500 millisecond. Okay, as you see now, because I am passing the output of this square wave clock with cycle of half second, I'm passing it to the input of the JK flip-flop. You see that the JK flip-flop is providing now a square wave with 1000 millisecond or square wave of 1 second. So by having a square wave with cycle period of half second, now we have a square wave with cycle period of 1 second. So half second cycle period of cycle, or cycle period, half second period cycle is now giving us 1 second period cycle square wave, because we are passing the output of the half second cycle period to the input of JK flip-flop. And that's what JK flip-flop does actually. Okay, now what I am doing here, let's go to the IDE integrated development environment. What I'm doing, guys, here is this is the timer. Remember, timer 6 is delivering for us a period or a square wave with cycle of 1 second or 1000 millisecond. Okay, I am taking this 1000 millisecond, and it's now this one is delivered at the input of timer 6. Okay, so if you go to the pin manager here, you can see that the CLC, the configurable logic cell number 1, I set the output to be mirrored on port C5 of this guy. Port C5 is this LED. The port C5 actually is connected internally within this development board to this LED, which is toggling on and off. Notice that the period of this LED is 2 seconds. 1, 2, 1, 2, 1, 2. Okay, and you can find out from here, because why? Because this period of 1 second, square wave of 1 second period, okay, it's being inputted, to here. Let me expand. The output of square wave 1 second period square wave, which is at this point is inputted to the OR gate, okay, and consequently it's passed to the clock of the J and K flip-flop. JK flip-flop. We are taking the output from Q, not inverted Q, and then the output, this output here goes to port C5, which is the LED, as we have seen before, right? So this one that is connected to the LED, okay? What happened is, as you see, now since this OR gate is not connected to anything, it's literally connected to ground, so the output will be grounded, okay? It will be grounded. But I, like by clicking on the mouse, I can change the state of the output from OR to NOR. So now it is OR gate, now it is NOR gate, okay? So by changing the status of the output to NOR, okay, so now I have an output of high because both of the all inputs here are low. So if I invert it, the output becomes high. The same thing for this guy, low, all of them low at the input, and I disconnected by just clicking here. By clicking, we connect and disconnect those connections. It's like similar to FPGAs, right? But this is, again, it's called CLC, configurable logic cells. So since all the inputs here actually are low, the output should be low. But by clicking on it and inverting it, now we have high. Notice that this gate 2 and gate 4, they have now high logic. And those high logic go to J and K. What that means now, J and K are configured as input high. So now we have input high. Let's go back to the hardware. This is actually by Texas Instrument. Okay, this texasinstrument.com. I'm using this one here. This one here is here. As you see, it is. Let me show it to you clearly here. Okay, this one. 107, it is 74 LS 107. So this 170, like the 74 family, 107 actually is a flip-flop, JK flip-flop. So which is this one? JK flip-flop, okay? JK flip-flop, this is the dual inline package. So the pin number 1 is J, and pin number 4 is J for unit 1, J like the unit number 1, J input for unit number 1, and K input for unit number 1. This is the output Q. This is inverted output. We don't want the inverted output. We just need the inverted output, or a non-inverted output, okay? This is now we are using the clock of the flip-flop. So we are using the clock of the flip-flop. Of course, we have the power at pin 14, 5 volts. I'm using 5 volts, a ground. And the J and K are both high. They are connected together. The Q is the output that goes to the LED. Remember, let me take you to the Q. This is the Q of JK flip-flop. This is the buffer amplifier actually within the microcontroller, the peripheral, okay? So this output of the Q of the JK flip-flop goes to the LED, okay? And that's what toggles the LED on and off. Remember that now, let me recap. The timer 1 actually, timer 6 is delivering a square wave with a period of 1 second or 1000 milliseconds. The output of this timer, okay, is being fed to the input of this OR gate, and now we have a 1 second square wave, 1 second square wave inputted to the clock of the JK flip-flop, and both J and K are put high, okay? So if this is in this status, you clock here the clock pin, then the LED connected to the output of Q, actually it will be toggled once every second. Okay, and that's what's happening here, right? If you go to, I'm using a 107L low Schottky 107A. So as you see in this condition, under this condition, if the clear is high, and if both J and K are put into high, and every time there is a clock on transition from high to low, when the clock transition from high to low, then the output Q will toggle. Okay, that's what's causing this LED to toggle. And this is like every programmer, baby. This is our baby program. Hello world, hello world, by using the FPGA built in within the microcontroller. Let's call it. Let's not cheat. I'm not gonna cheat on you, but I'm just giving you an idea about. If you are familiar with FPGA and would love to use FPGA with MCU built inside the MCU, and here is your dream coming true. Yeah, right. It's one of my dreams actually. So now you have the CLC, the configurable logic cell, configured properly as I explained to you, and that's this FPGA of the microcontroller, or actually this configurable logic cell is causing the LED to toggle. Okay, so now we are toggling this baby, the LED, with the configurable logic cell built within this microcontroller. Okay, as you see here, this is hardware. This one here, obviously, it is a JK flip-flop outside, like it's not built in, but it's outside this JK flip-flop from Texas Instrument 74 LS107. Actually is performing the same job. So this is hardware, and this one is done by configuring the CLC, configurable logic cell, of the microcontroller. Okay, so we can do it either by using microcontroller or the logic cells built within the microcontroller, or we can perform the same tasks by using an independent and separate JK flip-flop logic gate, like off the shelf from Texas Instrument, from OnSemi, or whatever, right? So what this one is doing, this microcontroller is generating a square wave with period of half second. When we pass this square wave period of half second to the input or to the clock of the JK flip-flop, this Texas Instruments 107 JK flip-flop, it delivers a square wave of 1 second period. So as you can see, I'm gonna zoom out now. Let's point finger at this one, on off, tick 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 tick, but this one tick 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 tick. As you see, this is slower. This is 1 second, and this is 1/2 second. So click tick 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 tick. This one tick 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 tick. Look, you can watch it yourself actually, right? This one. Every time this guy goes low, transition from high to low, this one flip states or toggles from high to low, or toggles from low to high. Okay. This one actually is following. This one is following the truth table of this one, which is this state of truth table. This is the truth table of large LS or low power Schottky 107, which is the JK flip flop. As long as you set the JK flip flop to this state, you will toggle on off the output, and assuming you are connecting it to, like, say 220 ohm resistor, and then to the ground. So you have an LED, the negative connected to ground, the positive connects to 220, and then it's connected, this one, the other side of 220 ohm resistor is connected to the Q non-inverted output of the JK flip-flop. Now you have what I'm having. Okay, of course, if you put switch instead, like if you instead of using this thing as a source to demonstrate the JK flip-flop, if you switch instead and you press the switch by your finger, because of jitter or because the switches and your fingers will deliver a lot of noise, this will turn on and off hundreds of times without even your eyes noticing it. So that's why it's really not good to use mechanical switch to make this demonstration, because mainly of the noisy mechanical switches, you have to use digital electronics in order to get clean square wave output out from the JK flip-flop. Of course, because why? Because the microcontroller, this one, is delivering a clean square wave, like half-second square wave, to the input of the JK flip-flop. Otherwise, you will see it turning on and off like at very rapid time, that to an extent that your eye will fail to observe that turning off and on for this one here. Okay, and this is called persistence of vision. Persistence of vision means your eyes, or our eyes, human eyes, actually they have memory. Okay, the memory makes them fail to observe rapid movements. That's why you see the cartoon and movies and the images in the TV and computer, they move very fast, that our eyes, because of persistence of vision, our eye is tricked into believing that those discrete images are actually continuous. Okay, because of, it's like memory, our eyes, persistence of vision, have memory. It deceives our brain into believing that those frames are connected, but they are actually not connected. They are discrete, but because of our eyes remember the previous frame, our brain is eluded into believing that the image is continuous or the movie is continuous. Okay, so that's why you have to use a source, like a clock source, clean clock source from microcontroller, in order to observe the phenomena of the JK hardware-based JK flip-flop. Now this is microcontroller-based flip-flop, which is configured by using the configurable logic cells, which is this one here. Okay, I hope you have found this one is useful. By the way, you know why we engineers used those kind of hardware, mainly because our C code, like most of the time I use C code, right? Most of the time our C code that is uploaded to this microcontroller, no matter how intelligent our code, the software or firmware, no matter how fast, even if we use interrupt request, sometimes there are certain things that go on with inside and outside the microcontroller, to an extent that the software or the code, the firmware code, fail to realize the processing of events. So sometimes we skip, it's unintentionally skip the events or the processing, and that could lead to disaster, especially if we are working with medical or military equipment. That could lead to a disaster, right? That's why we have to have hardware-based processings. Now this one in hardware, this one here can realize and recognize events with latency time, like on a nanosecond, like very rapidly. But because we are using C language, sometimes we are using Java. Good luck in Java. Good luck. It may never happen, right? But if you are using C, then it may happen. But if you are using assembly code, then it's more likely to happen, right? But sometimes it may not happen. How about if the programmer doesn't know assembly? Thank God I know assembly, but this hardware-based processing, right, and crunching on inputs, right, is much faster than the C code. Because the latency is defined as the time delay between the input and output of the hardware, whether it's driven by software or firmware, right? So the latency actually in here of the hardware is much shorter than the latency of microcontroller. Thus, whenever you are implementing or programming for very high speed processings and very high speed, extremely high speed projects, right, or feature implementing very high speed features, and you find out that your C code within the microcontroller fails to execute, then you better use the hardware logic gates, and that's why we need the hardware sometime. And this hardware is external, but the same hardware is implemented within the microcontroller. Isn't that beautiful? At the same low cost. It's like almost free. I mean, those guys, they are giving you free logic cells. Like, I would say, let me exaggerate. Those guys are giving you free FPGA, field programmable gate array, right? But let's call it CLC, because there are pros and cons to FPGAs and pros and cons to CLC. Let's not talk about it, because it's gonna take almost half hour now. This is, it's taking too much time. I will explain the difference between FPGAs and CLC, right? But I think that's enough to learn. Now you should be very dangerous if you know what is CLC and how we can configure it, and why we need it, why we need the CLC peripherals built inside the microcontroller that perform exactly similar as if you are having external logic gates, right? But now they are built inside. Why we need them? Because of high speed, because of multiple input processing, right? Because of parallel processing. Well, this one here can perform, seems to be parallel processing, but to our brain, to our human brain, because the period between one program counter and the next program counter within the PIC controller is very small, right? But in here, it happened at much faster, right? So now we have processing within this microcontroller. In parallel, we have processing within this hardware that's inside this one, okay? And guess what? The JK flip-flop or logic gates that are peripheral inside this peripheral to the core of this microcontroller, those configurable logic cells, CLCs, actually can have their outputs or inputs fed or delivered or to another peripherals like timers, interrupt routines, and like ADCs, DACs, and PWMs, so they can interconnect with one another. What that means, the logic gates, like such as JK flip-flop, that is built inside this microcontroller, can interface at the input level or output level to the other peripherals built within this microcontroller. Guys, isn't that amazing? It's really amazing, right? You can do like magic. You can do magic with those kind of things. This is really amazing, right? So I thought I will share with you one of the things that I have used for a while, right? And I think it's good to learn those kind of things, right? So as you see now, C5, okay, C5 is configured as output, and that's what C5 of 1619, that's what's toggling the LED here, okay? I hope you have enjoyed the thing and you benefited and you got something out of this mini presentation. If you have enjoyed it, if you learned something, please like, subscribe. I'm working hard for you guys. I don't need to do those kind of things, but it's good. It's good actually to have them in like safe. I look at them maybe in the next years. I look at them and I just remind myself, because we engineers do sound like I have thousands of different things in my head, right? Maybe in the next year I forget what I did. So by just looking at my video, I say, oh yeah, that's now I remember everything. So it's good for me and for you guys, right? So please like, subscribe, and share this video, and let the fun begin. Let everybody benefit. Thank you for watching. You have a great day.